we're going to move on to our next chapter in our series here, chapter 18. All right, and this is kind of a mixed bag of a bunch of different functional groups here. We have ethers, epoxides, thiols, and sulfides. All right, and we kind of throw these all together here because with the exception of epoxides, they're pretty boring functional groups. There's not a ton of reactions that we have here. All right, so first of all, let's just take a look at what each one of these functional groups look like. Right, an ether is our oxygen-based functional group, but importantly when oxygen is sandwiched in between two carbons. An epoxide is actually just an ether, but it's a very specific type of ether where that oxygen is arranged with those carbons into a three-membered ring. All right, and if you remember talking about cyclic alkanes before, you remember that these three-membered rings are super mad, right? They do not like, atoms do not like being forced into these three-membered rings because their bond angles are these non-ideal bond angles. Carbon loves to have a bond angle of about 109 degrees. It turns out that in this triangle here, it has to be forced to have a more acute bond angle of only 60 degrees. So the bottom line is these triangles are very unstable. And so we're going to see that even though this is an ether, it's a very mad ether. It's a very reactive ether because we forced it into this little triangle, and this little triangle really wants to break open. All right, so what we're going to see are ethers in general are fairly unreactive, but epoxides, which are just ethers, but a very specific type of ether, are very reactive. And we're actually going to focus most of our conversation on the reactions of those epoxides. Like fun fact, I don't know if y'all have heard of an epoxide out there in the wild. All right, but typically they would be used, you find them as adhesives, right? So when you go to Home Depot and you ask for an epoxide, you're really like getting this glue kind of mixture. And these epoxides, they always come in these containers that are kind of fancy where they have these two chambers. And in order to use them, you mix these two substances together and then it hardens into this very, very efficient, glue, what am I thinking? Adhesive, there's the fancy word I was looking for. All right, and bottom line is when you mix those two things together, you're kicking off this reaction of that epoxide that leads to that hardening, that adhesive reaction, okay? So anyways, yes, you may have heard of epoxides out in the wild as glues, as very fancy adhesives. All right, a thiol is kind of analogous to an alcohol, but with sulfur instead. If you notice where sulfur is on the periodic table, it's right underneath oxygen. So just like oxygen, it likes to have two bonds and two lone pairs. Thiols behave very similar to alcohols as well. They play kind of an outsized role in organic chemistry. One of our 20 amino acids, right? One of these building blocks of our proteins contains that thiol functional group. And so it's pretty important for organic chemistry and in particular biochemistry. And then the last one, a sulfide. If a thiol is analogous to an alcohol, a sulfide is analogous to an ether. So this is where we have our sulfur not with an SH group, but sandwiched between two carbons. Cool. All right, so these are going to be our topic of discussion. We're going to spend most of our time discussing ethers and epoxides. We're going to kind of mention thiols and sulfides, but not quite as much emphasis. All right. Again, we have our ether, so we have our oxygen sandwiched between two carbons. An epoxide is an ether, but specifically an ether that's been bent into that triangle, into that three-membered ring. We have our thiols, which are analogous to our alcohols, and then our sulfides, which are analogous to our ethers. All right, so first things first, we're going to start where we like to start for our compounds, and that's talking about nomenclature. All right, let's start with ethers first here. All right, so the weird thing about ethers is that they're treated not as functional groups, but as substituents in our nomenclature. All right, so let's take an example here. So step one, we have the same steps as always. We're going to find and name our parent chain. So how do we find our parent chain for an ether? Right, we have carbons on either side of our oxygen. So what we're going to do is we're going to chop at that oxygen, and we're going to look to see which one of those chains is the larger chain. All right, that one's going to be the parent chain of our molecule. So if I chop at my oxygen here, I see on one side I have these 4 carbons. And on the other side I just have this 1 carbon. So which one's going to be my parent chain in this molecule? The longer of the two, right? The 4 carbon parent chain. So for our parent chain, we're going to chop at that oxygen. All right, and the longer, or let's just say more carbons, okay, and remember these ethers, like I said, they're going to be treated as substituents. So there's not going to be any name or any ending to our parent chain that we tack on there. This is just going to be a butane parent chain. All right, so then how do we name that other portion here? We said we're going to treat it as a substituent, but how do we name it? So now when we get to our substituent section, our ethers are treated as a substituent, and the name of that substituent group, right? We have chloro groups and fluoro groups. So how do we name this thing here? It's going to be that number of carbon prefix plus the ending oxy. Right, so again, I'm going to treat this whole thing as a substituent here. And in particular, because it's 1 carbon, this is a methoxy group. All right, and then we're going to number and assemble our name just like we always do. So I'm going to number, I got to tell where on my parent chain that methoxy group is. So I'm going to go 1, 2, 3, 4. I see it's at locant 2, so this would be 2-methoxybutane. All right, I have my substituent on carbon 2 of my parent chain. That substituent is an ether, a methoxy group, a 1-carbon ether group, and the parent chain is that 4-carbon parent chain, my butane. All right, so the weird thing about ethers, you know, boring functional groups, so they're even relegated to being substituents in our nomenclature. They're not even given like the fancy functional group naming, right? We treat them as substituents, and we use that number of carbons plus that oxy ending. So let's just do a few examples here. All right, so I'm going to chop at that oxygen. Which side is going to be my parent chain, the left or the right? The right side. The longer of the two, more carbons. So my parent chain here is that propane. This whole substituent here, this carbon plus my oxygen, my ether group here, is going to be my substituent. This is a methoxy group. All right, 1 carbon. So meth is my prefix plus that oxy ending for our ethers. All right, and then importantly, don't forget you gotta number your parent chain as well. My methoxy group is located on carbon 1, so this is 1 methoxypropane. And yes, you got to include the 1 in the name because there's a different molecule that would be 2-methoxypropane, right? Just because it's on that first carbon doesn't mean that it's implied and we can leave it out, all right? I will say most ethers that we look at are linked on that very first carbon. Don't forget that 1 in the name, all right? Very common problem with ethers. I think when it's drawn like this, it's a little more obvious. So again, I'm going to chop at that oxygen. What's my parent chain, the top half or the bottom half? The top half, the longer of the two, more carbons. So my parent chain here are these 5 carbons, my pentane parent chain. And now the rest of it here is my ether substituent. That's 3 carbons long. All right, so when it was 1 carbon, it was a methoxy group. When it's 3 carbons, it's a propoxy group. All right, that prefix prop for 3 carbons. And then I'm going to make sure to include my numbering. That propoxy group is located on carbon 3, so that's 3 propoxy pentane. All right, again, ethers are kind of boring. What they're used for in the lab typically are solvents. They're not actually used in chemical reactions very often. They're much more likely used as just like your reaction medium, your liquid in which you dissolve something else in. Because of that, they're generally not referred to by their IUPAC names, but their common names. All right, so let's just take another example. Let's actually take our 1-methoxypropane. If we're doing our common names for our ethers. All right, what we see in our ethers is by definition there's a carbon, there's an alkyl chain on either side. All right, so when we do our common names, it's just alkyl 1 plus the other alkyl group followed by the word ether. Right, and we're going to arrange those alkyl groups in alphabetical order. So what do I mean by that? I'm going to look at my ether here. I'm going to look on either side of my oxygen. On the right-hand side, on the left-hand side is 1 carbon. So this would be a methyl group. On the other side are 3 carbons, so this would be a propyl group. And I'm just going to arrange these in alphabetical order, followed by the word ether. All right, so M comes before P in the alphabet, so this would be methyl, propyl, ether. All right, so our common name, unlike our IUPAC names, we actually have spaces in there. Right, so methyl space, propyl space, ether is our common name for this ether here. All right. So let me just move it elsewhere. All right, you guys are going to finish this off by giving me the common name for this ether here. Actually, let's do both. You're going to give me the common name and the IUPAC name for this ether here. right? So my common name, I'm just going to look on either side of my oxygen and name those alkyl groups. This is a 2-carbon alkyl group over here, so an ethyl group. This is a 4-carbon alcohol over here, not alcohol, sorry, 4-carbon alkyl group, so a butyl group. So putting it all together, alphabetical order, butyl, ethyl, ether. Okay, so now for my IUPAC name, I'm going to chop at that oxygen. I got to figure out which half is going to be my parent chain. All right, which half is my parent chain, left or right? The right-hand side, these 4 carbons here. So my parent chain is the butane. All right, I have these 1, 2 carbons in my ether substituent. So this would be an ethoxy group. All right, and then don't forget the numbering. We got to indicate which carbon on that parent chain that ethoxy group lives. So this would be 1 ethoxybutane. All run together, all one word. So my common name, butyl ethyl ether, or my IUPAC name, 1-ethoxybutane. All right. One more ether that gets kind of a special shout out here. Because it is by far the most commonly encountered ether. This has the common name diethyl ether. And it is far and away the most common ether that you encounter in the lab, so much so that they call this thing just ether. If you are ever reading a protocol and it says, oh, dissolve your solvent in ether, and you're like, wow, that is not specific at all. What ether are we talking about? It's specifically talking about diethyl ether. It is so commonly used that we just call diethyl ether, ether, and everybody knows what we're talking about. Cool. All right, we're going to go to one of our other functional groups. The other one we're going to spend some time naming is thiols. All right, we're not going to worry about naming epoxides. They're kind of weird. We're also not going to worry about naming sulfides. We're going to focus on naming thiols here. Thiol nomenclature. All right, and as opposed to ethers, thiols are functional groups in our name. So let's take a simple example here. All right, so now when we find our parent chain, we again got that longest continuous set of carbons with our functional group caveat. All right, and importantly, now that we have our new functional groups, we have our new suffix here, right? For alcohols, we use this suffix "ol" to end them. For thiols, we're going to use this, they got real creative, we're going to use the suffix thiol. All right, the functional group name is literally what we use in our nomenclature. Okay, so if I have this molecule here, for example, I'm going to find my longest continuous set of carbons that contains that parent chain. So my prop here. Let me just real quick swap out that oxygen, that sulfur for an oxygen, and let's remind ourselves how we would name this. This would be 1 propanol, right? Prop for the number of carbons, but we also have that AN in there to indicate that we have all single bonds. We talked about how to name alcohols that have a double bond in there instead. You would use an EN instead of an AN in your name. And then we have that ending OL. All right, so we're going to do the same thing. This is going to be 1 prop because it's 3 carbons. All right, but then I'm going to use that suffix thiol. And what do we notice that's wrong with this name here? Propanethiol. We got these 2 consonants that were run next to each other. And remember, we got rules that we're not allowed to do that in organic chemistry for whatever freaking reason. We're not allowed to put 2 consonants next to one another. So instead of being propanethiol, we're going to keep that E so that it's propanethiol. All right, so our thiol group's really nothing too crazy different, but we have to remember because our functional group name starts with a consonant, we're going to retain that E in our name. Also, again, I have to include my 1 because there's such a thing as 2-propanethiol, and that's a different molecule, right? So we have our locant, but again, when we do our parent chain here, we have to include that E at the end. So everybody take a second and name this one for me. All right, we have these 5 carbons in my parent chain. I'm going to number my parent chain so that that thiol group gets the lowest possible number. So this would be 2-pentane thiol. All right, again, I keep that E in my name so that I'm not running 2 consonants together. Pent because there's the 5 carbons, pentane because it's all single bonds, and then that suffix thiol because my functional group. All right, so last level, really our kind of secret goal here of introducing thiol nomenclature is it's going to be the first time that we see these molecules that have these 2 functional groups in there. So what do I mean by that? I mean, now we're going to talk about how to name something that has both a thiol group and an alcohol, a hydroxyl group. All right, we talked a little bit about this before with enols, naming molecules that had both a double bond and an alcohol group in there. All right, but this poses sort of a new opportunity, special challenge for us here. All right, like I said, all functional groups in organic chemistry are put on this scale of priority, right? So every functional group has been given a priority in organic chemistry, and they're all kind of ranked. We are going to look at now just a tiny subset of that, All right, here's our priority list. At the very bottom, our lowest priority groups are our alkynes and our alkenes, double bonds and triple bonds. Okay? Our highest priority group that we've discussed up until this point are our alcohols. Okay, we'll introduce some, basically we'll update this list every time we introduce a new functional group, but for right now at this portion of the course, our highest priority group is that alcohol. All right, and we can see that thiols sit lower on our priority list. I included one more here just for an example. Amines are lower than thiols on our priority list. So let's take that same example here. We have our 5-carbon parent chain. I want everybody to take a second and number this parent chain for me based on this list up here. So remember, when we're numbering, we're only going to pay attention to that highest priority functional group, right? So if I look at my list here, alcohols are higher priority than thiols. So when I number, the only thing I'm going to pay attention to is that locant for my alcohol functional group, that hydroxyl group. So I'm not going to number right to left, I'm going to number from left to right, right? Making sure that that OH group is on the lowest number carbon. All right, cool. So then there's this other aspect of this chart here. We got both suffixes and prefixes. What the hell? All right. We talked about alcohols. We use that OL suffix. And we just introduced nomenclature of thiols, where we use that thiol suffix. So what the heck is the prefix portion here? All right. When we get a molecule like this that has 2 functional groups in there, our highest priority group, we're going to use its suffix, but any lower priority groups are no longer considered functional groups in the nomenclature world. They are now relegated to just being substituents, which is going to use those prefixes instead. So in this molecule, I'm no longer going to refer to that thiol group as a thiol. I'm going to refer to it by its prefix, mercapto, and I'm going to treat it like a substituent in my name. So my lower priority group, I'm going to use its prefix, and I'm going to treat it as a substituent. Right, so no longer are you considered to be a functional group in my name. You are now a mercapto substituent. So when I name things here, I'm going to do just like I do for all substituents. I'm going to put that in the front half of my name. This would be 4 mercapto. 2 pentanol. All right, so we're going to build on this list as we introduce new functional groups throughout the semester here. But now we can see that we have our first example of having to use these prefixes to refer to our functional groups, these mercapto. So for the sake of practice, I want y'all to do one more for me. All right, parent chain, 1, 2, 3, 4, 5, 6, 7 carbons. We can number our parent chain from left to right or the other way. Which numbering scheme am I going to pick here, red or blue? Blue, because the only thing I care about is the location of that highest priority functional group, that alcohol group. Okay, and since that alcohol group is my highest priority group, everything else is treated as a substituent. I have this chloro group here. But now my thiol is no longer a thiol, it is a mercapto group. And when I put my name together, that mercapto group is just another substituent, right? It loses all of its kind of specialness because of that higher priority alcohol group. So when I put this together, I'm still going to assemble my name in alphabetical order. That means that my name will start with that 4-chloro, then the 6-mercapto, and then the 3-heptanol. All right, so again, if we have a molecule that has more than one functional group in it, the highest priority functional group is special. It's treated like a functional group in your name. The other one, the lower priority functional group, is no longer a functional group. It is now a substituent. It's got a special substituent name depending on what that was. So for our SH, that's a mercapto group. Okay, I got no idea where that comes from. The rest of them make a little bit more sense. For amines, it's an amino group. All right, but that's what the chemistry gods tell us. Importantly, on an exam, what you can expect to be given is a chart similar to this, with the exception I'm going to take out that suffix column, right? Or row, rather. You should know that thiols are thiols, that alcohols are ols, OL ending, right? We got to know the endings for our functional groups. What I will give you is the list of priorities, what is highest in priority, as well as what those prefixes are that we use to refer to those lower priority functional groups. Cool. And again, what we're going to see is we're going to introduce aldehydes and ketones next chapter, right? We're just going to continue to build on this list here of our priorities as we introduce more functional groups. Cool. All right. We're going to talk about one of our ether reactions here. This would be how you synthesize an ether. This is kind of your most basic method for creating ethers here. It only works for symmetric ethers. All right, and that is if we have an alcohol and we have it in acidic conditions. What we'll see is that two alcohol molecules will react with one another and create a symmetric ether. Okay. All right, we talked about our reaction mechanisms for alcohols, and we sort of specifically laid out acidic conditions mechanisms, right? This is also going to be an acidic condition mechanism here because I have that hydronium ion present. So we're going to see another acidic mechanism. And in our mechanisms, we need these proton transfer steps, right? So under acidic conditions, your acid, aka your proton donor, is going to be that hydronium ion. All right, and what is our base going to be? Is it going to be hydroxide? No, because hydroxide is way too strong of a base to exist under acidic conditions. But we still need something to be our proton acceptor in our mechanism. So we're going to use that weaker base, water. Okay, and if we have our alcohol group here, let's just look. In this reaction, we're going to need two of these guys to react with one another, right? If we look at our product, we have 6 carbons in our product. We start out with a 3-carbon alcohol. So we're going to have this reaction between 2 of them. How many of these oxygens are actually going to end up in my product? Only one of them, right? So that means the other one I got to lose. I got to get rid of one of these oxygens here. And we talked about how much of a pain in the butt it is to get rid of a hydroxyl group because they're such terrible leaving groups. So in every reaction to alcohol, our first step was some strategy to translate this into a better leaving group, right? And we had one common strategy that we used over and over again under acidic conditions, which was to do what to that alcohol group? Protonate it, to turn it into water, which would be a great leaving group, right? Absolutely. So, same thing here. We're going to have an acidic conditions mechanism where our proton donor is hydronium, our proton acceptor is water, and we got that same common strategy that we've seen, which is that we need to get rid of that hydroxyl group, and we're going to turn it into a better leaving group by protonating it. All right, so my first step in my mechanism here is going to involve that hydronium ion, and again, we're going to protonate OH to turn into a better leaving group. All right, so given where we're going here, I'm going to give you a little bit of a head start to see if you can't figure out what our mechanism is here. All right, again, a big portion of the remainder of this course is going to be mechanism heavy, and I want you guys to kind of be comfortable with them. Make some mistakes, try some stuff out, see if you can't get from A to B here. Just don't break these two rules that we have up at the top, right? We have to have our hydronium as our proton donor, and if there's any proton accepting going on, any base going on, we need to use water as that proton acceptor, right? Under acidic mechanisms, we should have no strong bases. No negatively charged oxygens in your mechanism. All right, for the sake of time, I'm gonna have to interrupt you. Let's talk this out here. All right, we're gonna say the very first step is to protonate that alcohol, turn it into a better leaving group. So now my oxygen has 2 hydrogens, means it's got a positive charge. This carbon right here is a primary carbon. So do we think that leaving group's just going to fall off as it is? All right, are we going to get a primary carbocation? No, we don't like primary carbocations. So we can't just have that leaving group leave in one step. We're going to have our nucleophile attack and our leaving group leave all in the same step here, right? We're going to kick off that leaving group, but importantly, it's got to be in the same step as we have that nucleophilic attack. So now we have our one alcohol reacting with its neighbor and kicking off that protonated leaving group. And this gets me pretty close, but I'm not quite done. I have my new carbon-oxygen bond, but importantly, there's also that hydrogen still bound. And how are we going to get rid of it to make our ether? Water, right? We're going to use our base. The only base that we're allowed to use under these acidic conditions would be water. All right, so fairly simple mechanism here, but again, the same sort of strategy that we've seen over and over again for our alcohols is we gotta convert it into a good leaving group. And so what we've seen is under acidic conditions, the way that we can do that is to protonate it, to turn it into a good leaving group water. So by protonating that alcohol, now we can kick off that OH. Our second alcohol molecule just plays the role of a nucleophile. It's gonna do the attacking here. When it does, it's got that proton still. We need to do a proton transfer step, and we're going to use our base under acidic conditions. We're going to use water to do it. And that leaves us with our ether. Cool. We'll pick up and talk more about ethers and epoxides next class.